Right, so now let's go ahead and look at this idea of concavity and points of inflection. So f of x is concave up if you have this kind of U shape here. So like a parabola that faces upward, you have this U shape. It could also be part of a U shape, so it doesn't have to completely form that U. It could be one side or the other side of that U. Also, f of x is concave down if we're looking at that upside down parabola shape, that upside down U, or parts of that upside down U were just kind of curves and forms that kind of idea of an upside down U. Our inflection point is just where f of x switches from that concave up to concave down or vice versa. It's that point where that flip actually occurs, right? So if we want to go ahead and find the open intervals where the function is concave up or concave down, we're given this lovely graph here, so no actual equation, and we're given the point 2, 3. So f of x is concave down all the way up from negative infinity, coming around until it hits this point 2, 3, which is our inflection point. And at this inflection point is where the turn occurs, and we're concave up from 2 to positive infinity. All right, so this is exactly where that actual switch happens from concave up to concave down. When we're doing our intervals, we do not actually include that x value of our ordered pair of our inflection point. We go ahead and disassociate that because that's the point where the actual turn happens. So we go ahead and use as an open interval, no brackets in our interval notation. And what we're looking for in our inflection point when we're talking about concave up and concave down is always our x value. It's never our y value. All right, so let's go ahead. We can use a second derivative test to go ahead and find the concavity in intervals as well as our inflection points. And our what we talk about is our f of x has an inflection point at some x is equal to c if the second derivative at c is equal to 0. And there's a switch of sign on the number line. So if we test a number to the left, test a number on the right, the sign actually changes. All right. So if we have a second derivative value here and some x value here at c, if we test it to the left, okay, then the negative, and to the right it's positive, or vice versa. This is where the concavity is going to change for us. Okay, so let's go ahead and look at an actual example using a function. So we want to go ahead and find out the intervals where this function is concave up or down and any inflection points. And we have a polynomial of f of x is equal to negative 2x cubed plus 9x squared plus 168x minus 3. Right. If we go ahead and take our first derivative is negative 6x squared plus 18x plus 168. We're going to go ahead and take our second derivative, which is negative 12x plus 18. Now remember, our inflection point is where this becomes 0, so we set this, our second derivative, equal to 0. And go ahead and solve. And so we go ahead and solve for it. We have negative 12x is equal to negative 18. X is positive 3 over 2. And what we're going to go ahead is test a value to the left and to the right of 3 over 2. Remember, 3 over 2 is about 1.5. And we are testing 0 on this side. You could test 1 if you wanted to. It's totally up to you. Right. And over to the left of 3 over 2, when we go ahead and plug in 0, we end up with a positive value. We end up with that positive value. So it is concave up when it is positive, from negative infinity to positive 3 over 2. If we go ahead and plug in the value 2 into our second derivative, we end up with a negative value because we have negative 24 plus 18. It's negative, so it's concave down from 3 over 2 to positive infinity. And in order to get our inflection point, we have to go ahead and plug our 3 over 2 into our original function. Up here with negative 2x cubed plus 9x squared plus 168x minus 3. And when we plug that in, we get a fraction of 525 divided by 2. Please leave it as an exact fraction if possible. If you have an inflection point as a fraction, go ahead and leave your y value as a simplified fraction also. Your calculator will go ahead and do that for you. Let's go ahead and talk about the formal definition of the second derivative test. So the second derivative test, if x is equal to c, is a critical number of f of x, then f of x has a max at x equals c if the second derivative of c is less than 0. So there's concave down. F of x has a min at x equals c if the second derivative of c is greater than 0, is concave up. And here's some visuals for you here. So here what we have is a second derivative. The y value at some x value c is less than 0, which means it's negative. It's a concave down, so it means it's coming up here. And the opposite if it's concave up. The test will actually fail if your second derivative at the value c is equal to 0. You might have an inflection point there, but you need a little bit more information. And because the second derivative is equal to 0, you will go ahead and back up and use the first derivative test in this particular case. So if we want to find some extrema here of this function here, right? We have f of x is equal to 3x cubed minus 3x squared plus 1. So we're expecting a sort of cubic function here. I'm going ahead and taking the first derivative. We get 9x squared minus 6x at our first derivative here. And we're going to set that equal to 0. And this is going to give us our critical points. So our critical points here, when we go ahead and factor out a 3x, x is either equal to 0, or 3x minus 2 is equal to 0, or 2 over 3. Okay, so we have two critical values at x is equal to 0 or x is equal to 2 over 3. All right, now we're going to go ahead and take the second derivative of that function. So taking the second derivative of 9x squared minus 6x, we end up with 18x minus 6. All right. If we go ahead and plug in 0 to that into that function, we end up with negative 6 is less than 0. So seeing as the value of our x is less than 0, we have a max at x equals 0. If we plug in 2 over 3 into that, we end up with the positive value of 6, and 6 is greater than 0. So we have a min at x value is equal to 2 over 3. All right, so we found our critical values using our first derivative. Right? And then what we do is we plug these values into our second derivative in order to go ahead and find our whether we have maxes or mins at those points. All right. And so we have a max at 0, 1. We have a min at 2 over 3, 5 over 9. Remember, your y values are coming from your original function.